All right, let's get going again.
I'll give it back to you.
Obviously, when you've got a railway travelling over very, very long distances, running that railway is basically about managing energy. Yeah. Energy is fuel, and fuel costs money. So, one of the important things is all about resistance to motion. So that resistance varies with speed, so that affects how fast the train can go. It affects the size of the locomotives you need, where those locomotives need to be put, how much fuel you take, and even what route you take. So let's have a look at this. This is a theoretical railway. You start from A and you want to get to B. Yeah? So one of the routes you might want to take is over the top, round the side, through a tunnel and across a bridge. So let's have a look at the one over the top first. Now it's the straightest path, yeah? Going straight over the top of the mountain. The problem with going over the top of the mountain is that this railway has to deal with one of the biggest problems that railways have to overcome, which is gradient or grade. What is gradient or grade? So in this country, we tend to talk about gradient, which is rise over run. So in old money, that's 1 in 8, for example. In America, and now in this country since about 1970s, we tend to use the word grade, which is the rise over the run, but as a percentage. So 1 in 8 is 12.5%. 1 in 10 is 10%, etc. Yeah? Now on any piece of track that goes up and down all over, yeah, there will be a thing called a ruling gradient, and that is the steepest piece of track in that route, if you like. So if you look back at this, that's probably this one here. Yeah, because if it can get up that one, it can get up this one. Yeah, so they have what's called a ruling gradient. The steepest one of those in the UK is the Lickey Incline, just outside Birmingham, which is at 1 and 37.7. Okay? To contrast that, we've got Brunel's billiard table. So between Didcot and Swindon is 1 in 660, and between Paddington and Didcot is 1 in 1,320. That's why it's called a billiard table. Typically, maximum ruling gauge in the UK is 1 in 100. That's the Settle Carlisle line. People know that one. Most railways are now 1 in 200 or less. So why does grade matter? Well, if you think about it, for a grade going uphill, this loco's got to pull it all up. Yeah? And as a rule of thumb, it takes 9 kilos of tractive force to pull a ton up a 1 in 100. Now when you've got a train hundreds of wagons long with literally thousands of tons of weight, that number can become very, very big. And if this gets too steep, the loco physically doesn't have the power to pull it up it. Yeah? Now you might say, if we can spend all that energy going all the way up to the top, surely when we get to the top we get it all when we come back, down the other side, get it all back. That would be the case if there wasn't things like speed limits. Or curves or whatever, which means you need to brake. Brake means heat, wasted, bad use of energy. Yeah. But what you'll find is that going over the top is rarely the best choice. So let's still look at another route, where you go around the curves on a nice even contour. So there's no grade on that route at all. Yeah? There are lots and lots of curves. So, we measure the radius of a curve in this country using this good word called radius. Very sensible idea. The Americans aren't like that. They somehow measure the number of degrees for a 100-foot chord. Still don't understand why they do that, but anyway, I've got it in both money here. So American 1 degree curve, just that, yeah, has a radius of 1,750 metres. Just to contrast that, the Japanese bullet train has a minimum curve radius of 8,000 metres. That is not very steep. Go up to 5 degrees, which is pretty much the typical practical limit for fast running in this country. That's 350 metres and an absolute minimum of 150 metres. Yeah. Now the thing about curves is the curves add drag. You know we said earlier about the squiggling as it goes round the corner? Well, that's the flange rubbing on the inside of the rail. Rubbing, not good in engineering, that is wasting energy. Yeah. Plus you'll find that all of these have speed restrictions. So what you're finding, you're constantly accelerating, decelerating, accelerating, decelerating for each of the curves. Yeah? For each degree here, so for each one of these degrees you increase it, you add half a kilo of resistance for every tonne of the train. So if your train weighs hundreds of tonnes, that's an awful lot of resistance you're adding to it. If you go up to 5 degrees, that resistance quadruples. If you go up to 10 degrees, so less than this one, it quadruples again. So what often happens is that, depending upon obviously the number of the curves and the degree of curvature, you may find that going around all the squiggly curves uses just as much energy as going over the top. But sometimes you'll find that these are just too expensive to conquer with grades and curves, so when you build a tunnel or a bridge, that is actually cheaper than trying to operate trains around here. Obviously, if you've got a train going over here once a year, that's fine. But if you've got 10 going over every day, that's a lot of money you're wasting in fuel.
Why not build a tunnel down the straight one?
It's an example. It's an illustrative example. Now, this is not a real railway, all right? Yes, Roger.
Occasionally, you have to go over the top.
You do?
If you go to Canada, there's a wonderful place called the Kicking Horse Pass. And when they first built the track, the gradient of the track was so great that they had a lot of runaways and they had to do something about it. So they built the spiral tunnels.
Yeah.
And the trains come up, they go into the side of the mountain in a great big loop and come out again, go across the other side of the valley into the mountain on the opposite side for another loop, and then they carry on along the
The thing is there not a loop, a climbing loop on the Welsh Highland line?
yeah, and
There used to be, if you're not...
It's not a Festinio to get around where the lake used to be, that's just to get a bit of height.
Yeah.
there's one in New Zealand too, on South Island. But when the trains are so long, they go into the tunnel, and the front end of the train comes out again before the back end has gone in. It's fantastic.
Yeah, I mean, I remember going on the one on the Festinio, and you can see that.
Yeah.
You're up here and the back's down there.
Yeah.
Anyway.
I was on a railway in Australia called the Zigzag Railway, and that literally zigzags down Brunswick Hill.
So, you might think all this talk about grades, curves, tunnels and bridges and all the rest of it, but even just running on a flat, level piece of track, yeah, without changing a speed, uses energy. Now, obviously, in a perfect world, all your axles and stuff will be frictionless devices, and obviously an object already in motion carries on going unless an alternative force is acted upon it, etc. Sadly, we're not in a perfect world. So there are several sources of rolling resistance to a train running along a normal level track. The first one is mechanical resistance, and that depends purely on the weight of the train. So that we're talking about things like friction in the bearings, deflection of the wheels and the tracks. Steel is stiff, but it's not infinitely so. They still do squish together a little bit, like a tyre does on a road. There's velocity-dependent resistance. So that's the faster it goes, the more resistance you get. And that's an example of that is things like ride quality. So you get wagons swaying from side to side and jostling and all that sort of stuff. And the faster you go, the more they do that and the more energy they waste. And then you've got air resistance, so that's drag. Obviously drag on both the front, the sides and the back of the train as it goes along. And the thing about these are linear, so you double the speed, you get double the resistance. With air resistance, you double the speed, you get 4 times the resistance. You add all them together, and you get the total resistance, yeah? Now that said, that is still incredibly low, okay, in comparison to any other form of transportation we've got. And that is the reason we use trains in the first place, and not lorries or cars or motorbikes or whatever, to travel lots of things around. That. Right. So all modern locomotives use traction motors now. As Mick and Mike told you a while ago, they're either diesel electric or they are direct electric, which gets the power through pantographs and catenary wires. So these things have a diesel motor that drives a generator. That generator generates electricity, which drives a traction motor. This just sucks electricity straight in and drives a traction motor. Yeah? The benefits of traction motors is there's no gearbox. It's just a motor. It's like an electric car. There's no gearbox. You squeeze the accelerator and it goes faster. Take your foot off, it goes slow. However, you are obviously with all of these still limited, if you like, by the rating of the motor, how powerful the motor is. And that, to some extent, is how big you can get into these. They are restricted by size. So, power, this is where I'm going to get mathematical on you here, right? It's force times velocity. There you go, that's as complicated as I'm going to get. If we draw a graph, okay, of the speed of the train against the tractive effort or the amount of traction is needed, force that's needed to go in there, you get an inverse relationship like this. The faster you go, the less traction you need. Okay, but this isn't quite right, okay? Because there is a physical limit to how fast the train can go. We have speed limits. If you go too fast, the train comes off the rails, etc. Yeah, so the graph gets cut off at this end. But there's also a limitation on the slow end as well. So, even if a motor could generate more force at that slow speed, the friction between the wheel and the rail limits how much of it can be utilised. Okay? And that's called the adhesion limit. Doesn't matter how much you try and increase this, you can't. So this graph shows why it's a bit of a challenge. You can't use the full power that's been developed by this to push it along. And as I said earlier, friction. So friction is obviously the most important thing on a railway, both in two ways. So the lack of friction in all the moving bits is the reason why railways are used to transport huge amounts of stuff around rather than lorries. Yeah? But on the other hand, we rely on a lot of friction between the rail and the wheel, because if it didn't, it just slips. Yeah? So we want as much friction as possible there and nowhere else. Now obviously in some of the steeper railways you might use cogs or stuff like that. On our normal railway we are purely talking about the adhesive action of a wheel squishing onto a rail. Yeah, and as I said earlier, the typical contact patch is a 50p piece. I want you to visualise how much friction we're talking about between a locomotive wheel and a rail. If I were to stick a 50p bird to a wall and then suspend two family cars from it, that's how much friction is needed at a wheel-rail interface. That is a hell of a lot of friction in there. Now when it comes to friction, yeah, incredibly, when it comes down to it, friction is down to two things. There's the force, which is basically the weight of the train, pushing down into the rail, and then the actual friction between the wheel and the rail. Yeah, make sense? Okay. So rougher surfaces have bigger coefficients of friction. Smoother surfaces have lower coefficients of friction. Double the friction coefficient, you get double the friction. Double the weight, you get double the force as well. So that effectively gives you two knobs you can twiddle, if you like, to manage your tractive effort. You can either increase the weight or decrease the weight, increase the friction or decrease the friction. Now in reality, you don't have a lot of that. You can't do much with this knob. Because you get things like oil, grease, rust, rain, leaves on the lawn, wrong kind of snow, all that sort of stuff, yeah? That lowers or raises the coefficient of friction, which makes it harder to keep the wheel stuck to the rails. Right place. Again, I'm going to get complicated here for you. So if you take the steepest section of your track, the ruling gradient I said earlier, yeah? You take your highest force, which is tractive effort, you divide it by this thing called dispatchable adhesion, which I'll come to in a minute, and that tells you how heavy the weight of the train needs to be. Okay? So that's a very complicated term, dispatchable adhesion. It basically just means it's the friction coefficient for a specific locomotive under a specific condition. So, for example, a new locomotive running on dry rails, that might be 30%, and that kind of old locomotive on frosty winter morning is 18%. You obviously can't get the same out of that as you can out of that. Having said all of that, we all know that's not set in stone, because they use sandboxes, where they're putting sand. I think, was that in the newsletter or something, or the WhatsApp group, wasn't it?
What was that?
That's what the WhatsApp group, where they're literally spraying sand between the wheel and the rail to increase that friction coefficient. So you do have a little bit. Now there is another way of turning that particular friction coefficient knob, but it's a little hard to explain, but I'll have a go. So, that's the wheel, that's the rail. Okay, wheels going round, rails. Okay, as the wheel goes along, what actually happens is here you've got maximum adhesion, but at the front and the back you get less adhesion because it's starting to slip. And if you exaggerate that, it starts to slip more and more and more until it lets go. And at that point it slips. So at the front you get slip, the back you get slip, and in the middle you get stick. Does that make sense? Yeah? Glad that makes sense to you. Now obviously all of this happens simultaneously, alright? And it's happening in a very, very continuous process, if you like. Now one of the actual fascinating things about this is that this stick slip means that the wheel is actually moving faster than it goes along the rail. Yeah, I know. This effect is called creep. Okay? Now we draw a graph. If we draw a graph of creep against the traction, you get this lovely curve. Yeah? And obviously when you've got no traction, you've got no creep. Makes sense. As you go up through the amount of traction, you get more creep. You get a bigger patch, the patch gets smaller, it creeps more. If you can imagine that zone I showed you of where it's actually sticking is getting smaller and smaller and smaller. Yeah? Until you get to a point at the top where you've got maximum creep. And it doesn't matter how much more traction you put on, it just is slipping after this. Totally, 100% slipping. So the wheels just spin and spin and spin and never create any more traction. Now, of course, this is a theoretical situation under ideal conditions, which we know doesn't happen in the real world. And you're probably thinking, well, the dynamic, when things are already slipping, it makes it easier to continue slipping than if it wasn't slipping. So that's this thing called dynamic coefficient of friction, is less than the coefficient when it's not slipping. An example of that is a violin bow. You think what happens when you draw a violin? It sticks, slips. Sticks, slips. And that's what makes the string vibrate, creating the noise. I won't say it's nice, but that's basically what's happening. That is a stick slip. Now obviously in a locomotive, it's not necessarily very desirable. It can lead to corrugations in the rail. It's a notorious problem that used to happen with steam locomotives, where the traction was varying and wherever it was as it goes round in its cycle. It's not constant on a steam loco. If you think about it, when the piston's at one end, you're creating no traction at all until it starts moving back the other way and then it goes back to zero again. So you're constantly oscillating the traction. Modern traction motors, it's constant. Yeah. So in the real world, the graph looks like this. Once you get to the maximum, it then comes lower down because of the dynamic coefficient of friction. Now in modern locomotives, with very sophisticated control systems that's monitoring each wheel individually, what's happening at each individual wheel, they monitor it to keep it here. That's where you're getting maximum efficiency out of that adhesion. Eking out those few more little percentage points can make a big difference when you're doing thousands of miles in terms of the amount of fuel you use. Does that make sense? Yeah. Good, I'm glad it makes sense to you. It didn't to me when I first looked at it. So.
But that only applies to driven axles?
Yes.
Yes.
Not yet, right.
Only ones with traction motors.
Right.
Right, lastly, let's go a bit more completely opposite direction. We'll talk about level crossings. Okay. Now, if you think about it, I don't know whether anybody's really thought about this too much, because I certainly hadn't until I started looking at it. Pretty much any vehicle you use on a day-to-day basis, you can see further than your stopping distance. Yeah, whether it be a car, a motorcycle, a bicycle, whatever it is. Yeah. Within the time it takes you to see that hazard, you've got enough time to realise there's a hazard, slow down and stop before you hit it. Yeah? Another way of saying that is your sight distance is longer than your stopping distance. Make sense? Yes. Now you may think that's pretty obvious, but it's a critical thing for man-operated machines. And it's not true for trains. Yeah? Whilst the driver can see as far as the rest of us can, the stopping distance for a train can be as much as a mile. Certainly some of these massive, great big freight wagons, So that basically means that if the driver can see it, it's too late. Yeah? You can't stop in time. So engineers have had to develop a lot of safety infrastructure to allow for that deficiency. So if you think about a level crossing, we say that trains have the right of way and cars have to stop for obvious reasons, because of the stopping distance and nothing else. And there's a litany of warning devices that enforce that right of way and avoid collisions. Detecting an oncoming train and giving motorists enough time to stop. Safety either cross it before the barriers come down or stop in order to allow the barriers to come down. It may sound simple, but the actual engineering that goes into that is quite complicated. So it's inevitable that railways cross roads. Anybody want to guess how many level crossings there are in the UK?
2,000.
20,000.
No, it's 6,000. There's 6,000 level crossings. And that's basically a place where trains and cars share the same bit of land. Yeah? So next time you stop at a level crossing, you'll now think about them very differently once I point out all the safety features that are there. So firstly, trains have warning devices like headlamps and horns, which they sound whenever they come across one of these, a whistle board. They are particularly common when you get no barriers. So when you're out in the middle of the sticks somewhere and you get a footpath crossing. Or what are called user-worked crossings. I love it.
User works.
And crossings have passive warnings that don't change, no matter what's happening. So you've got things like a danger sign, you've got keep crossing clear, you've got this thing called the crossbuck. That is an international symbol for a railway crossing, apparently. You also get cross hatches. You'll be familiar with seeing all these now, but how many of you actually noticed before? You just go across a level crossing, don't you? You're probably more familiar with the more active things, like the barriers coming down, yeah? But there's also lights that go amber and then red to warn you a train's coming. There's an electronic bell that sounds every time. Pretty simple, but the consequences of getting it wrong can be deadly. Yeah? Level crossings are now considered one of the most dangerous things on our road. In the UK, apart from potholes. So much so that creation of a new level crossing in this country is now illegal. Did you know that? I didn't tell them to this, to be honest. And that's part of the reason why things like HS2 cost so much. In the old days, they'd have put a few level crossings. You think how many roads HS2 must be crossing? Or East-West Rail, or whatever are the ones they're building. Yeah? Well, they're not allowed to put them on level crossings anymore, so they have to they either have to build a bridge or an underpass, which costs a hell of a lot more than a level crossing. Now, when it comes to the automated systems, first part of this process of closing all the barriers and flashing all the lights and whatever is detecting the train's actually there in the first place. Now, a lot of crossings are still done manually, either by a man in the signal box, increasingly rare these days, a man sitting in a control office somewhere looking at a camera, doing the same job as the signalman was, or automatically detecting the train. These are the other way. And they use things like this called relays. Basic old technology. Basically, you have a current that goes up one wire, through the relay, keeping it energised, down the other wire, down the other rail. As a train comes along, it short-circuits that, de-energises the relay, which activates all the stuff. Yeah? Triggering all the warning devices and signals and stuff. They might sound a bit convoluted for something as simple as that, but the reason they do that is it's simple, doesn't fail very often. It's basically, if you think about it, when you lose power, the relay de-energises and everything fails safe. Why it assumes there's a train coming, which is kind of a lot worse than assuming there isn't a train coming, and there is. Yeah. So if you look at these gates, they're actually electrically held up. So when the power fails, they automatically drop. Yeah? Which is obviously a much more preferable one than leaving it up when the train's coming. You want them. Now, one of the problems with all of this, though, is that as human beings, we are naturally dubious of automated processes. Yeah? So every time a level crossing activates and no train comes, people lose trust in it. And then they might start to do things like going round the barrier or whatever, or waiting too bloody long, or whatever, yeah. So failing safe is not enough. You have to maintain them properly, because if you don't, people get killed. One of the things to consider is where do you put that detection circuit? Yeah. If you put it too close to the level crossing, there ain't enough time for a car already on it to get off, or for a motorist to stop when the barrier drops. If you put it too far away, the motorist sits there going, where's this bloody train then? Where is it? And they might get bored and decide that it's not coming and go round anyway. Yeah? So too much time can actually make the crossing unsafe. It's a bit weird. So when next time you're sat at a level crossing, just think about, take a few seconds to think about all of those safety features and the amount of engineering that's gone in to trying to keep you alive so that the train doesn't hit you. So that's the end of my talk tonight. There are lots of other things I could have talked about, but I ain't got time or the energy at the moment. Maybe somebody will do another talk on some of these bits. Yes, Mark.
Sunningdale Station again, I think, is the only crossing, level crossing, at an angle. And in the days of the old mechanical gates, the nearer set on the smaller axis had to have cams to delay one gate so that the other could pass it. And the poor old signalman had to do that with a hand wheel.
Not many of them left anymore.
So if it's Germany, the train stops for the cars. Is it Germany?
Don't know, couldn't tell you that.
Yeah. Yeah. What about maglev? You know, that's the future, isn't it? No rails.
Maybe.
The Japanese are going absolutely full bore for it, aren't they? Big time.
If you want to know more about this, I can definitely recommend the YouTube channel, Practical Engineering. He did a whole series on this, and I've nicked a load of his videos in this. Really interesting, good guy. Does a lot of other stuff on engineering as well, but I have to give due acknowledgement of what I've nicked. So,
There's a good website, the RAIB Accident Investigation Team. They've got a really good website. And if you're interested in level crossings and accidents, have a look at them. They're really, I won't go into it, but some really interesting ones on there.
well, that's it.
Okay, any more questions for Guy? Okay, let's show our appreciation.